And welcome to my Lab 2 report, Charge Tapes Revisited. In my previous lab, we estimated the charge on a piece of clear tape by treating it as a single point charge, but now in this lab we're going to produce a sophisticated computational model by treating the tape as a line of evenly distributed charge. As a brief preview, my new line charge model calculated the total charge on the tape to be 2.017729 e to the negative 8 coulombs. Physics principles. First, we got Newton's second law because the top tape is being levitated and it's in equilibrium. Second, we have the electric force, and third, we have the charge density / superposition principle. So we mathematically break the tape down into tiny pieces and calculate the E force by summing them all together, or integrating them. Okay, so quick preview on lab 1. We got two tapes. We got this base tape and we got two U tapes, and we ripped them off of the base tape. So they roughly have the same charge, right? And this charge is positive, by the way. That really shouldn't matter. So they both have the same charge. So that must mean that they're going to repel because likes repel. So here, one of the tapes is suspended on two supports and another tape is trying to push it up. And as we can see here, the tape B, which is the system, it's levitating. And we know that the system's in equilibrium because it's not moving. So this implies that the electric force pushing up must be exactly equal magnitude to the gravitational force pulling it down. And the distance it was repelled was this, 0.017 meters. So all the rest of these initial conditions, they don't really matter. And the main experiment with lab 2 is now that we're using the line charge model, we want to make a computational model to help us plug and chug a Q value into the line charge model to make the magnitudes of the electric force and gravitational force equal. So I'll show you guys what that means. Okay, so real quick, we have 3 sections of code here. So block 1, it just defines my E field function. So I was kind of confused about this at first, but think about it as like a calculator. You put in information that it asks for, and it calculates it for you. In this case, it calculates the E field, and that's what's going on here. You just put in the source of the charge and the space you want to measure the field at, and it spits out the E field at that space. Now, block 2, this is where we apply the charge density / superposition principle, and this is a master loop that adds up every single tiny interaction between the two tapes. So line 111, we start an outer loop. We grab one discrete piece of the top tape to act as our observation location. Now, these two lines, 112 and 113. We initialize the electric field at the specific location to 0 and set up a green arrow to visualize later. Now line 115, we start the inner loop while holding that one piece of top tape. We iterate through every single piece of tape, every single piece of the bottom tape. Okay, line 118 and 119. Let's see. So for each bottom piece, we use the E field function to calculate the tiny electric field it creates, and we add it to a running total for the top location. And then 122 and 123. Once we have the field, we multiply it by the charge of our top piece to get the electric force. Then we add that force to our master running total, which is F underscore E underscore on underscore top. And then here we just scale, and the loop ends. And lastly, block 3, we just have the arrows showing the force of the electric force and the gravitational force, which is mass times gravity, downwards. So this is what it looked like. As we can see, these are equal. Model assumption. So make the model work, we had to make assumptions. We ignored air resistance. We assumed that both tapes had the exact same amount of charge. We assumed that the charge was evenly distributed, and we only took 100 small DQ samples. But in reality, there's a lot more than that. Now, potential sources of error in my data include charge escaping in my hand or the environment, and human error in eyeballing exactly 0.017 meters with a ruler, because there's no way you could accurately see how far up it went with the eye. So now what if? So the what if question: what if you had modeled each of your tapes as a single point charge like the previous lab? Then they asked to compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you got when you use your line charge model. So I got Q equals 7.937 e to the negative 9 coulombs when I used the point charge model, and here I had to plug and chug in order to make these two equal, and the value that worked was this. And so yeah, the values are here. Now the question asks, do these estimates differ? Yes, they obviously do. And which value is more likely to be closer to the real value, and why? So I think this is going to be lab 2 is going to be more closer to the real value, so the line charge model. It's because it's just a more realistic value, I guess. In the point charge model, 100% of the charge is concentrated directly above the other charge at distance d. But in real life, and especially in this experiment, it's not the case. Like look right here. In the experiment, we laid out the tape flat on another tape, so its whole surface is going to get a charge. And as we rip it off from the other tape, as we rip it off from the other tape, the whole surface is going to get some sort of charge, right? It's not just one little point, which is what we assumed in this model, the point charge model. So that's probably why the assumption that the charge is spread out evenly across the tape is actually not a bad assumption. It kind of makes sense here. Okay. Thank you.